take it you need to get permissions. Give me 1 second. All right, no, you should be good to go. All right, good morning, everyone. Today is September 1st. This is day 2 of 1.05. We have bell work today. I think going forward, we should have most days we'll have bell work. So this is from yesterday. We have to use the PQ list to create our list of possible routes. And that's all we have to do for this first problem here. And Noah's doing that for us. So this is saying plus or minus, he has 1 over 1, plus or minus 1 over 2. Actually, this is a pretty big list, right? No, I take it that you have either a digital pad to write on or you have a touch screen like I do. You have neither. You're writing with your mouse. Now that is impressive. Now that is impressive, writing with a mouse like that. So while Noah's doing that, I'm going to help him and reduce the one. So I'm going to do the next line for him while he's creating that first line to save time because there is actually quite a bit to write. All right. All right, no, and then what's your final line? I should have told you to do that last line while I was doing that second line for you. Yeah, this one had quite a bit of writing. You got to make sure that when you do this, just like yesterday, you write them all out like you did in the first line, and then you need to reduce everything. And then your final line is just writing all of the numbers one time. So whenever you have duplicates, well, just write it once. Class, do you agree with his answer? Yeah, I think I do too. At quick glance, I agree. All right, class, in chat, what are the zeros of this polynomial function? What are the zeros? Ooh, so we have 5 twice, right? Because it's a multiplicity of 2, it's called. So we have 5 twice, -2, and +2. Very good. Very good. So we only have to write this. Oops. We only have to write that one time. So like on a quiz, on a test, you would just say, your zeros are x equals 5, even though it occurred twice, only put it once. -2, and then +2. That's what you would write for those are your zeros. Those are your solutions. Someone's on mic. No? Okay. All right. All right. Nice job, everyone who worked those out. All right. Let's get started to today's lesson. All right. This is from yesterday. I'm going to skip it. Just, I don't know why I have it there. All right. Descartes or Descartes. I don't know. We'll say just Descartes' rule of signs. So we're going to determine the bounds of positive and negative roots of the polynomials. And we're also going to determine how many positive and how many negative possible roots there are. All right, make sure your paper and pencil out. All right, so you can go ahead. So this is in your module. You don't have to feel like you have to write this down on your notes right now. If you want to snip it now, you can, but it is in the module. So I'm not going to pause too long on this page, but I will go through it and explain it. So again, if you need to write this down, check the module. All right, so the Descartes' rule of signs. So we have one for positive roots and we have one for negative roots. So the one for positive roots says the number of positive roots, or remember zeros mean the same thing, is less than or equal to the number of sign changes for the terms of a polynomial. Now, you may have understood the first part, but the second half, you're like, well, I need to see an example. And so I'll show you one. And it's using Descartes' rule of signs is super, super easy. Super easy. And this is the same rule for negative roots, but we have to do something to the function first. We have to plug in negative x for all of the x's in our polynomial and then simplify first. And we'll see that in my first example. But it's the same thing. It's just the number of sign changes determines the possible negative solutions. And then this last part, super important, and I'll explain on our first example when we do it, that for each case, whether we're talking about positive or negative roots, the number of roots is less than the number of sign changes then it differs by a multiple of 2. So what that means is, let's say we have a total of 8 sign changes. Well, it could be 8, or it could be 6, it could be 4, it could be 2, or it could be none. So multiples of 2 going down from the max. Let's say it was maybe possible positive roots was 5. So it could be 5, it could be 3, it could be 1. It can't be 0 because it's not a multiple of 2, right? We have to go down by 2 every single time. And so we have to stop at 1 because we can't say, oh, there's -1 possible solutions. Well, that's impossible, right? All right. So then we have the upper bound and lower bound theorem, but I'm going to come back to this one. Let's actually see this in action. And then we'll talk about this next theorem, the upper and lower bound. This first one, super fast, super easy. This one is kind of tedious. All right, so just to show I don't know, some random example that I'm going to do, right? So we're going to do this, and then I'm going to do this, right? So, all right, just random, right? So positive real solutions. Well, positive real solutions. Well, we have one positive real solution. This one has 2. So if we're using Descartes' rule and we're given the polynomial instead of the graph, we would say that negative real solutions, we would say 2 or 0, right? We have this all multiples of 2 going down. So 2 and then 0. Upper bound. Well, so looking at this, the upper bound, count how many it is. 1, 2, 3. So it looks like it's less than 4, right? Looks like it's less than 4. So the upper bound would be 4. And then the lower bounds, that's right there at that x-axis. So that looks like it's 1, 2, 3, 4, 5, 6, 7. A little past -7. So that means that -8 would be the lower bound. So graphically, that's what it is. And that's what we're going to calculate mathematically, not graphically. All right, we all doing good on what these terms mean? Positive solutions, negative solutions, upper and lower bound. All right. So let's actually see the Descartes rule of sign in action. So this is how I do it. I think this is an easy way to demonstrate sign changes. So what I don't think is a good idea is to just try to look at it and count. Well, positive, negative, then back to positive, then negative again, then still negative, and then positive, and try to count how many times we flip flop. So this is what I do. And I think it's a good idea to see it visually so you don't make a mistake. So going from this is positive, 5x to the fifth. So it goes positive to negative, back to positive, back to negative, stays negative, back to positive. So what I do is every time we flip flop signs, I just do a little curve, right? If it's the same, like going from negative to negative, I just do a straight line because there's no change, right? And then we just count how many humps we have. 1, 2, 3, 4. So we could have a maximum of 4. Or what else, class? What else? So if it's not 4, what else could it be? 2, or what else? 0. Yeah. So the question in chat was, uh, scroll up here. So why is it 2 or 0? Well, because Descartes' rule says, going back to this right here, it says that it has to be multiple of 2. So less than the max, but multiples of 2. So we just keep decreasing by 2. And mathematically, it just works out. He figured it out that if you were to graph this, or if you were to factor this, it would cross the x-axis either in 4 places, 2 places, or not at all, based on sign changes. So using this rule determines how many times we're going to cross the x-axis, or in other words, how many times we're going to have solutions that are positive, or roots that are positive, or zeros that are positive, right? Remember yesterday, they all mean the same thing? So there should be 5, but there are only 3 roots. Is that why we use the multiple of 2? I can't really answer of why it's multiple of 2. It just, that's the theorem. That's what the theorem says. And looking into why it's multiple of 2 would be like a proof class. And that's not what we're doing. And it sounds really complicated and long to figure out how he figured out it's multiples of 2. I don't know. Maybe he saw a pattern. But good question here, right? All right. Now for the negative part. Remember I said we have to plug in negative x into all of the x's and simplify first? So that's what we do. So my first line here is I am replacing all of these x's with negative x. So I got negative x here, negative x, negative x, negative x, negative x. So pretty simple. So class, a negative to an odd power, is that going to become positive or negative? Negative, yep. So that's how we get negative 5x to the fifth. All right, the next term. A negative to an even power. Positive or negative? Positive. Yep. So this becomes positive, but it's negative, so it just stays negative, right? All right, next term. The negative x to the third power. Positive or negative? Negative, yeah. And so forth, right? And so forth. So we just go through and we simplify. Now this is not hard, but if you don't show your steps, it's easy to miss a sign, right? Especially if it's already negative, like this right here. Negative squared is positive, but positive times a negative still stays negative. Over here, we have negative times a negative becomes positive, and that's, of course, just carries down as plus 120. All right, is everyone good so far on plugging in the negative x and simplifying? All right, good. All right, next we do the same thing. We count the sign changes. So looking at, so we got negative to a negative, no change, to a negative, no change, to a negative, no change. Oh, to a positive, it flips. And so we're positive now, and then back to another positive, so no change. So how many negative roots should we find? Just one. Just one. Now, can it be 1 or 0? No, it cannot. Remember, multiple of 2. So remember, 1 minus 2 is negative 1. You can't have a negative amount of negative roots. That just sounds super weird and doesn't work. All right, so this is used. So this right here is using Descartes' rule of signs. Super straightforward, right? So let me, I'm going to skip ahead because I was going to kind of bounce back and forth between the two rules and the theorems, but let me have all of you practice. Pretend you didn't see that page. Everyone practice this one. So let me give you, a moment to write it down, and then let's say a minute. I think a minute is more than enough to do the first one, right? For positive roots, we'll do that one. So 1 minute to do the top half of the screen. All right, time is up. So class, how many positive roots could we have? Remember, you got to list all of them. Just putting. So we got 5, 3, or 1. We got 4, 2, or 0. 4, 2, or 0. So we're kind of looks like we're split, right? Looks like we're split. Let's take a look. So we have positive to a negative. That's a sign change. Negative to a positive, another sign change. Positive to a negative, that's another one. Negative to a positive, that's another sign change. And then positive to a negative, that's another one. So we got plus, minus, plus, minus. Yeah, it keeps flip-flopping. So that's 1, 2, 3, 4. Ooh, that's 5. That's 5. So I'm going to have to say that the 5 3s and 1s have it. 5 3s and 1s have it. Now, here's a question for people in chat. If you did not get this one correct, did you do this visual marker to show all the sign changes like I did, or did you try to just count them out? So help me understand where some of you are maybe not counting correct. What's going on? All right, no, fair enough. So yeah, so it's gonna be so we count. We all can see that we have five sign changes, right? So it goes plus to minus. There's your first one. Minus to plus. There's another flip flop. Plus to minus. There's a third one. Minus to plus. There's your fourth one, and then plus to minus. So that's five sign changes. One, two, three, four, five. So the most positive roots that we can have is five, and it's multiples of two. So from five, we just subtract two. Five minus two is three. Three minus two is one, and then we have to stop there because we can't go negative. All right, is everyone good now on this one? Good, good, good. All right. Now I'm going to give you all, I think we'll say, how much time you want? A minute or 2 minutes for this second part? What do you want in chat, guys and girls? 2 minutes? Okay, 2 minutes. You got it. All right, 2 minutes to plug in negative x, simplify it, and then identify the sign changes. Make sure you show your work. Skipping steps is a good way to make mistakes. The problem is it's supposed to be covered. So it's your job to plug this into the original function. So it's the same function. You're just plugging it in. Yeah, my cat's a bully. She wants me to follow her to the kitchen so I can give her some cat treats. She does it every morning. And if I don't, she's going to terrorize me the entire time and walk all over my stuff in front of the screen. Another 13 seconds. All right. So, all right. How many negative real roots can we have? Two or zero. Two or zero. Let's see if I agree with you. Two or zero. I do not agree with you. I got zero. Camille got zero. Ryan got zero. So let's see if we simplified. So the only way I think you can miss this one is if you didn't simplify correctly. So this is the setup, right? And we should have got this, right? negative. Oh my gosh. Negative to the fifth power is still negative. So a negative times a positive is negative. Go on to the next one. Negative to the fourth power is positive. Positive times negative is negative. Negative to the third power is negative. Negative times positive is negative. Negative squared is positive. Positive times negative is negative. Negative times positive is negative, and then our negative 175 carries down. So if you look, negative, 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 negative. There are no sign changes. No sign changes. That's why it's 0. Ah, all right. All right, see how much time we have left. We'll come back to this one at the very end. So I want to go to the next half of this lesson, which is, in my opinion, the harder half. So that's the upper and lower bound. All right, upper bound. Oh boy, this one's sounds confusing. So for a positive number, c, if f of x is divided by, well, the binomial form, right? So if c is a solution, x minus c would be the binomial, right? And the resulting quotient, meaning the quotient is the answer to the division, and the remainders have no changes in sign. So all what does it say? So all non-negative terms or all non-positive terms. Then f of x has no real roots greater than c. That sounds so confusing. This says the same thing for lower bound after you flip the signs. Now, this second part of this lower bound theorem gives you an alternate method to calculating lower bound. Now, I don't like doing it this way, so my examples today will not do this second way of doing it. I will only be doing this first way of the lower bound. Yikes. All right. So let's look at what that means. Upper bound. So it says division, right? So we have to do synthetic division to find out the upper bound. So we have it set up. I already put in all of the coefficients here. Now to do this is tedious. You always start at 1 and you go up. So let's check 1. Drop the 5 times 5. So I'm going to stop right here because what we need all of these to be positive, or in other words, non-negative. We need all of these to be non-negative or non-positive. And the reason why they say non-negative or not non-positive, because 0 is okay to have. It's 0 is neither positive nor negative. So that's why they say all non-positive are all non-negative. So right now we have 1 of each. So I'm going to go ahead and back up. So after you try 1, whoops, I don't know why. The undo you would think would actually undo everything I just did. It doesn't. Then we try 2. So we drop the 5, of course. 10, negative 15. Well, 2 doesn't work either because I just got a negative. All right, good enough. So you have to, it is tedious. You have to go through all one, start with 1, then go to 2, then go to 3, and so on until we find the right combination. So the right combination, just to save us the pain of going through 6 of them. So 5 doesn't work, 6 does. So 6 would be where it actually works, and I'll work that out. So we drop the 5. 6 times 5 is 30. Minus 25 is 5. 30. 44. Uh-oh. What's 6 times 44? Anybody? It's a really big number. 264. Okay. What's 264 minus 70? 196. What's 196 times 6? Anybody typing it in for me? 1176. Oh, somebody says it's 194 for the previous step. Oh, let me. And 194 times 6 is what? 1164. Go with that. And then 1164 minus 24 is some other really big number, right? And then that big number times 6 is an even bigger number. So we can see that, without me even finishing this part, that all of the numbers are all non-negative numbers. So that means that 6 works. So this is the upper bound, which means if you were to graph this polynomial, it would cross the x-axis at 6 or below. That's what that upper bound means. All right, now for the lower bound, we do the exact same thing. We have to, just like before, we got to replace x with negative x and simplify it. So that would be probably the hardest part in this problem. And then you are starting with 1 and going up. So I'm pretty sure all of you are going to have a question like, well, why isn't it negative 1? I'm going to answer that in a moment. So we're going to start with 1. We're going to do the same thing. So we want all of these to be non-positive, right? So either all non-positive or all non-negative. So we want all non-positive numbers. So drop the negative 5 times that, negative 30, negative 30, negative 44, negative 44, 7, 8, 9, 10, 11. Oh, what's negative 114 plus 24? Math is hard. Is it negative 90? And then so look at this. We did all that work and we got a positive 30. Yeah, that's sad, right? So we almost had it. We had negative, negative all the way down, and then we got a positive at the very end. So 1 doesn't work. That is a bummer. So we have to try the next one. So we would try 2. And I believe 2 does work. Just to save us the pain of going through that, it 2 does work. And I do have the work on this next page to show that, just to save time. Now, to answer people's probably question about when we check this, we still start with 1, we go to 2, we go to 3. We only check positive numbers, but whatever we get for the, if it checks out, which 2 does, let me go to this next page. If 2 checks out, which it does, right? We have all negatives here. So this works. So this is talking about lower bound. So lower bound will always be negative when you write your answer. So you have to make it a -2 when you actually write it here. Very tedious, right? All right, how are we feeling about this? Other than the fact that it's tedious and we have to kind of go through. Now there is maybe an easier way to do this. What's maybe an easy way that we could maybe start at a higher number? Any ideas of that might save us a bunch of time? Like given your test and you had to find the upper and lower bound, what might be an easy way to try to get us to the right answer? Not well, maybe the coefficient. I don't know. So I don't know if that coefficient would help us or not. I'm going to say maybe not, but I don't know. I don't think that is going to hold true for everything. Any ideas of how we might be able to help us better select numbers to check? Any ideas? Any ideas? We did this yesterday. We did this yesterday. Dun, dun, dun. No other ideas, huh? What about graphing? What if we graphed and we can actually see where it crosses the x-axis for the upper and lower? You think maybe that might help us narrow it down? Oh yeah, yeah. So like a quiz or a test, and you have to find the upper and lower bounds. Maybe graphing it, and we can see it visually, and then we can test numbers. So remember, don't believe a graph because sometimes the upper bound might be one whole number higher or lower than what you see visually. That I've seen that happen on problems. So maybe on when you see it on the graph, you say, oh, it crosses at like 5.2. Okay, so the upper bound must be 6. Check 6. Don't just put 6, check 6. It might not work. Maybe not. It's a good guess. It probably will, though. So check 6 mathematically. If it doesn't work, then check 7. You're probably going to be good. So that's a kind of a fast way to really narrow the upper and lower bound down. So yeah, it's a good way to save time, but you still have to do the synthetic division to verify. Yeah, so on your tests, on your quizzes, absolutely, you're allowed to use Desmos, you're allowed to use calculator, graph paper, all that stuff. Yeah, you're welcome to do that. Yep. All right, so let's look at this one. So yeah, these can be super annoying. So I'm going to give everyone 3 minutes to find the upper bound. 3 minutes. And feel free to check in Desmos first if you want, and then confirm mathematically. That's okay. And then as you go through this, if you just do it, synthetically versus graph in chat, once you checked a number, you write in chat, this number doesn't work. This number doesn't work. And that way people in chat can see that too and maybe help them out of ones that you've already checked to save them the grief of going through it. So to enter in Desmos, like for example, you would put 2x and then you would do that little caret button. And when you hit that, shift and whatever was that, shift 6, it'll put like an exponent in Desmos. And then once you type that in, use the arrow to the right to do, plus or minus the next term, whatever. Could you use Desmos, whatever his name is? No. So using Desmos to figure out the possible positive or negative roots would not work in Desmos because Desmos is going to show you the actual positive or negative roots, not the possibilities. So, for example, let's say Desmos showed you crossing the x-axis twice, but let's say Descartes says you could have 4, 2, or 0. Well, Desmos is not going to let you know that it could have been 4, but it's not. See what I'm saying? Oh, okay. So could you use Descartes' rule to check for numbers in the upper and lower bounds? No. So Descartes' rule only tells us how many solutions will be positive or will be negative. All right. Anybody have a solution for the upper bound? 5? You got 5. I would agree with you. Yep. I would agree with you. So, Elizabeth, did you try 5 first? So 6 will work, of course, but did you check 5? No. Okay. So I'm glad you made that mistake because if you select a number that is too high, for example, let's say you overshot it by, in this case, 1. The answer is 5, but you chose 6. 6 will work absolutely. And remember, this upper bound, doing this rule tells us that no real solutions will be above that number. That's what we're doing. So by putting a 6 for the answer, you are correct. However, there's a better answer. And if you check 6 and it worked, you should have checked 5 to make sure it didn't work. Because like 7 will work, 6 will work, 5 will work, 4 will not work. So that means 5 is the upper bound. Zero's allowed, yeah. Yeah, ignore all the zeros. They don't count as positive nor negative. No, that's a good question. I didn't bring that up. Yeah, if you get zeros, it's okay. It's okay to have zeros. Do I have these worked out? I don't have them worked out. Well, I'm just going to show the math with 5. Oops. Oops. That should have been a 2. My batteries, my mouse are going out. All right, let's try it again. Drop the 2. 10, 0, 17. Ooh, 35, 5, 6, 7, 85. Uh-oh, 35, 25, 15, 17. Yeah, so zeros are okay. Yeah, so they're all non-negative or non-positive. So yeah, they're all non-negative, right? So remember the word either all non-negative or all non-positive. So they're positive or 0. They could be positive or negative for the second half. But yeah, all non-negative, all non-positive. No, good question about zeros. All right, lower bound. All right, this one is actually super easy. Let's do 1 minute. We'll finish this one up. Yeah, this one's super easy. Very little checks needed. Can it be 0? Because that's all. So the way this rule works, we have to start with 1. Good question, though. I actually wondered the same thing, and I had to look it up. So we don't start with 0. We have to start with 1. But yeah, I think 0 also works, even though we can't start there, right? All right, class. What is the lower bound? Looks like we got a lot of people saying it's -1. I would agree with you, -1. So remember, lower bound is always going to be negative. Upper bound will always be positive. Never check 0. Never check 0. And before your test, I will verify, because sometimes the exams or even the quizzes will do their own thing and not follow the rules and will give a different answer. And I've seen that before. So I will double check before the exam to let you know. All right. So yeah, -1 works. So for this problem, we always start at, 1 and we check. If 1 didn't work, then we would just go to the next number, right? We go to 2, then 3, and so forth. So in this case, we want all non-positive numbers. So 1 times -2, -2, so -12, -12, -29. Uh-oh. -29 minus 85. 8, 9, 10. What is that? 100 and something? Someone help me out. 114. Times 1. -114 minus 35. What is that? -149. And then, yeah, so we can see pretty clear that, whatever that is, right? Negative something or other. -324. Okay. Yeah, so we can see that they're all non-positive numbers. So 1 works. So that means the lower bound is -1. So, all right, how are we feeling about the upper and lower bound stuff. Tedious, yes. The hardest part, I think, is this just setting this second part up and replacing all the x's with negative x and simplifying. That's probably the hardest part, and that's where the mistakes will occur. But again, given your test and you put your answers, always graph it to see if your answer kind of correlates or fits the narrative of what is going on graphically and what you did mathematically. Let's see if there's that story connects in some way. If it doesn't, like let's say you clearly see it crosses the x-axis at -5, but you're saying the lower bound is -1. Well, something's not right? Because the lower bound should be less than where it crosses the x-axis, right? So always check graphically, especially on a quiz or a test. Yeah. All right. So I have, this is another example. Go ahead and write this down, and maybe on your own time you can work this out, and I will show the answer. Yeah, to save time, I'm just going to show the answer for this one. Go ahead and write it down and work it out later if you'd like. I encourage it. But this one should have either 2 or 0 positive real roots. And it should have either 3 or 1 negative, real roots. So work that out on your own. So same problem from the previous page, but now this one wants us to find the upper and lower bound. So same thing, just work this out on your own time. I already set up the 2, but you should get the upper bound being 2 for the first one, and for the lower bound should be -3. So again, work these out on your own. We had a question earlier about, will this coefficient tell us the upper bound? No. So in this case, you see that it's a 5, but the upper bound is actually a 2. So I guess that idea that this could help us out is false, right? All right. So why is it important? So I guess I say here, the purpose of this lesson here is to give us, like tools to help us narrow down solutions, help us understand more about the roots or the zeros and the characteristics, not to actually solve them for the roots, right? This is just to help us narrow down real solutions, not to actually solve it. So the different characteristics. Why does it differ from the graph sometimes? What do you mean? Lower bound was -1, but when I graphed it, it crossed the x-axis at let's go back to that one. Let's check. So you may have just entered it wrong. Which one was that? This one right here? So did you so you didn't graph this one, did you? Like you don't want to graph this. This is just to use the rule. This is the original function. So this is what you should be graphing right here. This one right here. Is that what you did? You graphed the wrong one? Okay, fair enough. All right. I'm glad you brought that up. That is a great question. So remember, when you graph it, you're graphing the original function, right? This is the original function that we care about determining the characteristics. We only flip, our x's to find our lower bound. So that's why we do that. We should never ever graph what we get here. That won't tell us anything except confusion. So no, great question. I'm glad you brought that up. I will make sure to bring that up in the is it the 10:30 class that we have, or that I have for the other students. Great question. All right. Any other questions? Can upper and lower bound be expressed in inequality? No. So, and the reason why is because if you write an inequality to express the upper and lower bound of that function, that really pertains to the domain or the range. And the domain could be infinity, from negative to positive. So you want to avoid writing an interval or inequality form because it's confusing. Yeah, it's just confusing. Now, I guess you could say, if you really wanted to, the possible real solutions is on the interval, and then write the interval. If you actually state it before the interval, I could see that being appropriate, and I would understand, and I know that you understand that those are just the solutions and not the domain or range. So the definition of bound. So let's go back to the very beginning and my little graph here, right? The upper and lower bound. So these definitions here talk about real roots, right? Real solutions, meaning it has to cross the x-axis, right? If it doesn't cross the x-axis, those solutions are either they're probably complex, right? Also, you could have, yeah. So it has to be real. I almost went on a tangent there. Real roots. So crosses the x-axis. So the bounds tells us, like on this one right here, this one crosses at like just after -7, right? So between -7 and -8. So the lower bound is -8 here. So that means that the lowest real solution that we're going to have is at -8 or higher. And then for the upper bound being 4, we're just below 4, somewhere between 3 and 4. So the upper bound will be 4. This tells us that the positive real solutions will be at 4 or lower, but not greater. So that's the definition in a nutshell. All right. Any other questions before we stop? It's like I think we're out of time anyway, right? Yeah, we're out of time. So, well, guys, thanks for coming. And as always, I hope you learned something, and I will see you tomorrow. Tomorrow Thursday already? Tomorrow's going to be Thursday. Wow, this week is just flying by. It feels like these weeks just fly by. So, all right, everyone. See you all tomorrow.